Hello folks, we're talking about kinetic rotational energy in this problem. This is number 35 from the back of the chapter. We have an 80 centimeter diameter, 400 gram solid sphere is released from rest at the top of a 2.1 long 25-degree incline. It rolls without slipping to the bottom. A. What's the sphere's angular velocity at the bottom? And B, what fraction of its kinetic energy is rotational? So tackling part A, so we have a small little picture here. We got our sphere, we got some height here that we don't quite know, but we know the length of this entire incline, and we know the incline is 25 degrees. To find the sphere's angular velocity at the bottom, it's actually really hard to do this just using torques. It's darn near impossible. So we need to use energy. And when we see something like this, where we're rolling here from some height down to some other height, already we should be thinking about using energy, because we're turning potential, right? Some gravitational potential energy into our kinetic energy. And not only do we have some rotation, but we also have translation here. So it's a little bit of a complicated scenario here. But first off, we can solve for h, right? That'll be useful to us. H is going to be this side of our triangle. We know the hypotenuse is what? We know the hypotenuse is 2.1 meters. Let's try that again. 2.1 meters times then, right? This is the opposite side, so we need to use sine of 25 degrees. And when we do that out, we get 0.887 meters. That'll be our working height for this problem. Now, this is an isolated situation. There's just enough friction to roll this thing, but not enough to actually worry about work done by friction to take energy out of our system. So our delta E is equal to 0. Whenever we say it rolls without slipping, we are just considering a small amount of friction to actually get it to roll, and that's about it. Unless we say something else about friction, we can just assume this. So what do I have initially? Well, I have some initial potential energy due to gravity, right? UGI. That then needs to be converted into some kinetic energy down here, right? We're going to assume that there's no gravitational potential energy down there. I'm going to just set that. So I have some K total. Right, and K total, we've said before, is not only the translational kinetic energy, but also the rotational kinetic energy. So let's kind of continue this out. I have some mgh of my sphere equals 1/2 mv f, or v, and I'm actually going to say v of the let's just say VF. Normally I write this as V center of mass, but we can just write it as VF for right now, plus 1/2 I omega squared, and omega F squared. So, I want to know what the angular, right, the final angular speed is, so I don't want to work in V, I really want to focus on this omega F. So let's turn our VF into omega F by saying 1/2 mr squared times omega F squared, right, plus 1/2 I omega F squared. In my notes, I actually point this out in my notes. I haven't pointed this out explicitly in lecture because it doesn't really come up a whole heck of a lot, but where we are on our rotating sphere or cylinder matters when we're taking into consideration this conversion from V into omega. At the tippy top of the sphere, so something like right here, I'm actually going to be twice the translational speed, or the speed of the center of mass. Whereas right down here, I'm actually at rest, right? And that's because our pivot point is actually down here, right? And if I'm pivoting around there, I'm not moving. So that is a condition of rolling, and it's a little bit odd. I put that in my lecture notes. Take a look at that at some point. But for now, we can keep on rolling. So now I want to say that this is equal to mg. H, I want to take omega f out of this situation, divide by the rest of it, right? So I can say 1/2 mr squared plus 1/2 I of a sphere times omega f squared. I can divide both sides by this term in the parentheses and take a square root. If I do that, I get mgh over 1/2 mr squared plus the I of a sphere. I probably should put that in at some point. 2/5 mr squared. And I'm using lowercase m and lowercase r, but I don't have to. I'm kind of just doing that off the cuff. I forgot 1/2. Shouldn't forget that 1/2. So I want to be careful about that. Another way of going about this, though, is I could get rid of this 1/2, get rid of this 1/2, and just say 2 up here. That's perfectly fine. And if I do that, what I can say then is square root the whole entire thing, and this is equal to my omega f. Right? So let's actually plug in some numbers here. If I plug in my mass is 0.4 kilograms, my height is going to be this 0.887 meters, and the radius is going to be 0.4. 0.4 meters, because we're in centimeters, and we gave you a diameter, so you got to divide that by 2. I get an answer for this omega f equal to 88 radians per second. And radians per second, remember, that is our unit for angular velocity or angular speed. Does that make sense for us? Yeah, I think it does. I think that works out quite nicely. So that's part A. That's part A. What about part B? What fraction of its kinetic energy is rotational? So for this, I need to know what the total rotational energy is, what the total kinetic energy is, and then what the rotational energy is for part B here. So K rotational is equal to 1/2 times that 2 over 5 mr squared times my omega squared. Right, this is our I of a sphere. And if I use the 88 radians per second, right, that's what we'll put in. We'll hold off on that for just a second. I have a feeling that this is going to turn out quite nicely, but the 2 and the 2 are going to cancel, so I'm left with 1 over 5 mr squared omega squared. Okay, what about K total? K total is equal to 1/2 mr squared omega squared plus 1/5 mr squared omega squared. Whew, wait, what? Let's take a step back. All right, a few things. This guy, right, is 1/2 mv squared, but I've taken the liberty to convert the v squared into r squared omega f squared, just like we did in part A. And then I've taken our result from up above and just plugged it in, because our total is equal to K trans plus K rotational, right? So if I add this up, the least common denominator here, it's going to be 5/10 plus 2/10, so I got 7 over 10 times mr squared omega squared. It's weird looking, but that's our total kinetic energy. So now I'm saying, what is the ratio, essentially? What is the fraction of K rotational over K total? if I write out our expressions, I have 1 over 5 mr squared omega squared over 7 over 10 mr squared omega squared, right? This is why I said let's hold off on putting the omegas and everything in, calculating. I know that we like to use numbers, but sometimes we can just make our lives so much easier when we just hold off for a second. So omegas are going to cancel, r's are going to cancel, m going to cancel, right? And I'm left with 1/5 over 7/10. That actually turns out to be 2/7, which is approximately 28%. So 28% of the total kinetic energy of this thing is locked up in the rotational aspect of it. The rest of it is going to be the translational kinetic energy. But that just kind of is a quick example of how to approach translational and rotational kinetic energy in terms of a rolling ball kind of problem. We shouldn't always just jump to torques. Think if we can use energy. Does it feel like an energy problem? Does it feel like an energy problem that's just rotating? If so, try out the translational and rotational kinetic energies. See how that works out for you. If you have any questions with this, you can always email me or come to an office hour. Happy to talk about this. Otherwise, have a good one.